Welcome to Module 202A on Introduction to Series AC Circuits. We're going to look at the properties of different types of series circuits. We're going to be covering three different types of series circuits, and it's going to be split into three different videos. Our first video is going to be based on resistive circuits, so this is going to be more of a review of your first year material. One thing we should remember is the fact that current is constant inside a series circuit. So when we look at our phasor diagrams, we'll find our current on our reference line. And also, remember, since we're going to be looking at inductive and capacitive circuits, we need to remember that inductive circuits are lagging circuits, capacitive circuits are leading circuits, and we need to represent those in our phasor diagrams as well. Let's start by reviewing series resistive circuits. Let's look at this example of a series resistive circuit. In here we have three different resistors of different values. One thing we should remember from first year is the fact that resistances in series are additive. That means R total is equal to R1 plus R2 plus R3. And in this case, that is 100 ohms. The other thing we have to remember is the fact that Kirchhoff's voltage law also applies to series circuits. Kirchhoff's voltage law states that voltage rise must equal total voltage drops. So my voltage rise being my supply needs to equal the voltage that I can read across each one of my resistances, all added together. So the voltage of R1 plus the voltage of R2 plus the voltage of R3 is going to equal 120 volts. The other thing we should remember is that voltage and resistance are directly proportional, which means the bigger the resistor is, the bigger the voltage drop across that resistor is as well. When we look at the impedance diagram for a purely resistive circuit, one thing we should recognize is the fact that there is no reactance. That means my total Z equals my total R. My impedance is my resistance. This is why stating Ohm's law as E equals I times R works, because R and Z are the same value in a purely resistive circuit. And since they are the same value, my phase angle is 0 degrees, which means my power factor for a purely resistive circuit is 1. When we are looking at our phasor diagrams, once again, our reference line is going to be our current. So I total is always going to be found on our reference line. Anytime that you see a phasor diagram where I total is on the reference line, that means we're looking at a phasor diagram for a series circuit. With resistors, my phase angle for my resistor is 0 degrees, which means I have a power factor of 1. This also means that all my voltages for each resistor should be also shown on the reference line. Here we have VR1, VR2, and VR3. Since Kirchhoff's voltage law applies, where VR1 plus VR2 plus VR3 is equal to my supply voltage of 120 volts, when I show that on my phasor diagram, the length of each one of those phasors should add up to the total phasor length for my V total. When we are looking at the power triangle for a resistive circuit, since we have no reactance, that also means that we have no reactive power. This means that my apparent power and my true power are the exact same value. S equals P. We can also see that since all I have is powers, all my powers will add up, since they are all the same phase angle. So P total will equal P1 plus P2 plus P3. This is the end of series resistive circuits. Once you've gone through the video and your module, go back to Blackboard and do the knowledge check, and then you can move on to part 2.